Welcome back, everyone. In this lecture, I will actually prove the two versions of the structure theorem of finite abelian groups. They are equivalent. So we introduced both the versions in the last lecture. So let us recall both the versions. So here is the first version. So for both versions, let us assume G to be a finite abelian group. Okay, so the first version says G is isomorphic to the product of cyclic groups of prime power orders. Okay, so in particularly G can be written as Z modulo P1 E1 Z cross etc cross Z modulo P R E R Z. So note that these primes P1 etc PR, they are not necessarily distinct. Okay, so where this P1 etc PR, so not necessarily distinct primes. And first statement also says that something about uniqueness. Moreover, so these exponents, the list of prime powers, so they are unique up to permutation. Okay, P1 power E1 etc PR power ER. Okay, so this is a multi-set because PI's can repeat and exponents also can repeat. So this is unique. Okay, up to recording. So that means uniquely determined by the group G itself. So this is a multi-set. Okay, so this is your first version. So now let's look at the second version. Again, second version is easy to state. So now it doesn't involve prime powers, but it involves some choices of orders of the cyclic groups. So it says G can be written as product of again cyclic groups, call them A1Z cross etc Z modulo AMZ. So then these AIs, so they are uniquely determined satisfying this property. So where AI satisfies, so AM divides AM minus 1 and so on, then A2 divides A1. Okay, so moreover, the list of these natural numbers A1 etc AM. So this is again unique up to reorder. So now note that this also repetition can be allowed. For example, you can have like all the AIs are equal. Okay, so it can happen that Z modulo, like for example 2Z cross Z modulo 2Z cross etc Z modulo 2Z. So that can happen. For example, all AIs could be equal and it can be prime Z modulo PZ power something. Okay, so these things one should actually kind of carefully pay attention. So this can also be multi-set. Okay, so let us see like how one can go from one version to the another version. Okay, again all we are going to use is this basic fact that we actually recalled last time. So that can be recalled using, okay, that can be proved using this Chinese remainder theorem. So what this says, so if you start with Z modulo, let's say some M1 Z cross Z modulo some m2z and so on. It's a z modulo some mlz. So this is going to be isomorphic to z modulo m1 times etc. ml z if this m1 etc. ml they are all relatively prime. Okay. So if they are relatively prime, then if you take this product of cyclic groups z modulo m1 cross z modulo m2 cross etc. z modulo ml, then that will be isomorphic to z modulo the product m1 etc. ml z. So this is actually important fact. So one can use induction to prove this. Actually one can reduce this from the case L equal to 2. For general L you can use induction on L and then conclude this. Okay. So now what we want to see, okay, so let us try to understand how like second version actually can be obtained from the first version. So let us start with the first version. Okay. So the first version says so what is the first version? So G is nothing but Z modulo P1 E1 Z cross etc. cross Z PR ER Z. Okay. So now what we do, we simply actually collect those primes, okay, so that those are all equal. Okay. So fix a prime P, fix a prime P. Of course, among this P1 etc. PR, so that is sufficient. So then collect those indices from this 1 to R such that this Pi equal to P. Okay. So call this is some SI. So this SI can be some indices. Okay. For example, let us label them differently. So it can be some J1 etc. some J K Ki. Okay. So all these indices can be equal to this the corresponding primes Pi can be equal to P. Sorry, this is S of P. The prime P is fixed. So now what we will do, if you look at the corresponding exponents, then you can see that this Ej1 plus etc. plus Ejki. So this is going to be exactly equal to the exponent that you get it for P. So call that exponent is E of P. Okay. So you will be able to write the cardinality of G, call it capital N. So this capital N you can write it as, let us use this product of prime notation. So if you use this prime factorization, then N can be written as product of some prime powers in a unique way. So let us use this notation, product you take it over all prime P and then P power E of P is the prime factorization of this capital N. So call this is prime factorization of capital N. So then you can see that if you collect those I such that Pi equal to P, if you add the exponents, then you will get E of P. Why that is the case? Because the cardinality of G has to be P1 power E1 etc. PR power ER, which is exactly equal to product P power E of P P varies over prime number. Okay. So, note that E of P will be 0 for all but finitely many primes P. Okay. So, it is mostly 0. So, this is what you get. So, now what we are going to do, so we are actually going to take this highest exponents and then we will be actually kind of collecting them together. So, what we want to do, so we want to permute these indices so that this E j 1 is greater than or equal to etc greater than or equal to E j k p. Okay. So, you just permute them so that you arrange it in the decreasing order, because they are all just some numbers. So, you will be able to arrange them in the decreasing order. So, then what you can do, you can take this A 1. So, this A 1 is going to be again product over all prime. Now, what you do, you take this first exponent E j 1 of p. Okay. Again all this can be arranged it as E j 1 of p etc E j k p of p. Okay. So, this is what we are relabeling the exponent. So, we are calling it E j as okay, E j 1 as E j 1 of p and so on. Okay. So, the notation is kind of suggestive. So, now using this you can see that if you take the product of all those highest possible exponents for each prime p, so that is your A 1. So, your A 1 is nothing but this. So, then what will be A 2? So, the A 2 is the second thing. So, A 2 is again possible product over all prime p such that p power E j 2 of p. So, like this etc you can define them. Then from the definition it is clear that A 2 divides A 1 as E j 2 of p is less than or equal to E j 1 of p for all prime p. Okay. So, similarly, so you will be able to define the all possible A 1 etc A m. Okay. At for some m, so you will be having this non-trivial exponents. After that it is going to be 0. So, you choose that least m, so that you will be able to define A 1 etc A m such that this A m divides A m minus 1 and so on, A 2 divides A 1. Okay. So, now if you go back, so what is this A 1? So, this A 1 is nothing but product P E j 1 of P, where P runs over all prime P. Okay. So, then you can see that if you take the corresponding cyclic groups having that order, then the direct product of this G z modulo P power this E j 1 of P. So, this product over the prime P, okay, this is going to be just the finite product. Okay. So, if you use the direct sum notation, you can see that this is going to be the direct sum of all those things. So, then you can see that this is going to be naturally isomorphic to Z modulo A 1 Z, because once you run over distinct primes, then all those groups that corresponds to the cyclic group of that particular prime power order. So, those are all actually relatively prime numbers, okay, corresponding to the various prime p. It will be relatively prime. So, then if you take the product among them, then you can collect them together, you can make this Z modulo A 1 Z. And similarly, if you go to A2, again the same philosophy happens. You have this product over all prime power this A2 of P, then P runs over all prime. Then if you take the product of these cyclic groups Z modulo P E J2 of P, where P runs over all prime, you can see that this is going to be just Z modulo A2 Z, etc. Okay. So, this way you can shuffle them together, because we already know that H cross K is isomorphic to K cross H. Okay. So, you are allowed to permute these things whatever way you want. So, still it will be in the same isomorphism class of that same group. Okay. So, you just group them together, okay, and then you run over various primes and then correct exponents, okay, then you will get exactly the groups that you are interested in. So, the Z modulo A1 Z and Z modulo A2 Z, etc. And from the construction, it is clear that this A2 divides A1 and A3 divides A2 and so on. So, this way you are able to actually get the second version using the first version. Okay, let us do one example, then it will become very clear. So, here is the example. Okay. Let us take something like involving 3 primes. So, let us take Z modulo 3 square Z cross Z modulo 5 Z cross Z modulo 7 square Z cross Z modulo, let us say 5 cube Z, and then let us say cross some Z modulo 7 power 4 Z. Okay. So, all these things are of prime power order cyclic groups, product of prime power order cyclic groups. So, now we need to actually collect them together, so that A2 divides A1, A3 divides A2 and so on. So, let us see how one can does that. So, first what I said, you collect, so you pick a prime and then collect the exponents together. Okay. For example, if you take 3, you have only 3 square, and then if you take 5, you have 5 and then 5 square, 5 cube, and then if you take 7, you have 7 square and 7 power 4. Okay. So, the product of all this is going to be your group order. The cardinality of G is going to be 3 square, 5 power 4 and then 7 power 6. So, this is your order. So, now to get A1, what I said, you choose this order and then you write it in the increasing order. Okay. So, that is what you have done. So, now you pick this 4 and then this 3 and then the power of 2, that is 2. So, that is going to be your A1. So, your A1 is 7 power 4, 5 cube and then 3 square. So, note that all of them are relatively prime numbers. So, that means if you take Z modulo this A1 Z, it is going to be isomorphic to Z modulo 7 power 4 Z cross Z modulo 5 cube Z and then Z modulo 3 square Z. Okay. So, you can group these things together and then get this. So, you take this and then you take this and then you take this. So, these 3 things can be grouped together to get this bigger cyclic group. Okay. So, that you call it Z modulo A1 Z. So, now if you take these two, you can see that 5 and 7 square, that is what remains here. So, this can be combined. So, then you will get that A2. So, Z modulo A2 Z is going to be isomorphic to Z modulo 5 Z cross Z modulo. So, maybe I should write it in the increase 7 square Z modulo 5 Z. So, now you can easily see that G is naturally isomorphic to Z modulo A1 Z cross Z modulo A2 Z. So, now what is A1? A1 is 7 power 4 cross 5 power 3 cross 3 square Now what is A2? A2 is 7 square cross 5 power 1 cross 3 power 0. So if you look at the exponents, these exponents increases. So the respective AI should divide AI minus 1. Okay, so that's what happening. Okay, so A2 divides A1. So that's all we are doing to go from first version to second version. So now more or less now it's clear. So how to go from the second version to the first version. So to go from second version to the first version, so let us start with second version, okay, and then we want to go to first version. So how one does this? So let's start with the second version. It says G is isomorphic to Z modulo A1 Z cross etc cross Z modulo AM Z, where A1 AM divides AM minus 1 etc. A2 divides A1. Okay. So now what you do? You just use the prime factorization of all this A1 etc. AM. So now you can see that there will be only finitely many primes. Okay, let's call Q1 etc. some QL. So these are all the distinct primes. So distinct primes that divides all of them. Let's take A1. Okay, because AM divides AM minus 1 etc. A2 divides A1. So all the prime factors of AM etc. A2 must divide A1. So no issue. So now then you can see that this A1 can be written as now Q1 power, let's say E11, Q2 power E12 etc. QL power E1L. Similarly, A2 can be written as Q1 power E21, Q2 power E22 etc. QL power E2L. So likewise you can write for anything. So AM will be Q1 power EM1, Q2 power EM2 etc. QL power EM. Okay, so now you can see that since AM divides AM minus 1 and so on. So if you read it from bottom to top, so since A2 divides A1, you can see that the exponents are in the increasing order. Okay, let's compare the exponents. So you have E11, E21, EL1, E12, E22, EL2 and so on, EM1, E2M etc. ELM. So now if you read it from the bottom to top, so it has to increase. So this has to be greater than or equal to, this has to be greater than or equal to etc. greater than or equal to. Again similarly this has to be greater than or equal to etc. So this is the necessary and sufficient condition for AM dividing AM minus 1 and so on, A2 dividing A1. Okay. So you can rewrite in terms of this exponents. So now you can see that Z modulo A1 Z is naturally isomorphic to Z modulo Q1 power E11 Z cross etc. cross Z modulo QL power E1L Z. Okay. So now this is true for any A1 etc. AM. Okay, once you know the factorization, then you have this AIZ is isomorphic to Z modulo QI E1 EI1 Z cross etc. cross Z modulo Q, L, E, I, L, Z. So now because of this, if you take product here, so then you will be taking the corresponding product here. So that says that the G, which is isomorphic to the product of this, is going to be product of all this. So that is going to be just product of cyclic groups of prime power orders. Okay. And again, like I said, for certain primes you can arrange them so that they are indeed indeed decreasing in the exponents. Okay. So this is going to be m and then m. So these exponents are indeed decreasing. Okay. So this is something that is what we also did in the from first to go from the first version to the second version. We did something similar to this. Okay. So that way you can actually obtain the second version, sorry, the first version from the second version. So going from the second version to first version is not that hard, because once you know that, you can write I as product of some primes. So then the corresponding things is splitted into product of cyclic groups of prime power orders. So using that you can immediately conclude. Okay. So here you can see that we are repeatedly using this fact that if you take any groups, okay, let us take G1 cross etc. cross GR. So this is going to be isomorphic to G sigma 1 cross etc. cross G sigma for G sigma for any permutation sigma is in SL. Okay. So this is somewhat very important fact that has been repeatedly used in order to achieve all this. Okay. So this actually can be proved from the R equal to 2 version. When R equal to 2, this simply says G cross G1 cross G2 is isomorphic to G2 cross G1, and you know that any given permutation sigma can be obtained from the product of this adjacent permutation or the simple permutation I plus 1. So that means, so if you write sigma as product of the simple ones, sigma I1 etc. sigma Ik, where sigma I is some simple permutation or the adjacent permutation. Basically it is obtained from just switching j and j plus 1 for some j. So then you can see that, like, at a time you are only permuting some j and j plus 1. Okay. So from starting with G1 etc. GR, you go to like G1 etc. Gj minus 1, then you switch G plus Gj plus 1 cross Gj, and then you go to other components. Okay. So this switching only you do at a time, and then you can easily check that. So if 1 2 are in the correct order and then switch only j plus 1 and j, so then the corresponding groups will be isomorphic. Okay. So that can be easily checked from this isomorphism. So I will leave it as exercise to verify this. Okay. And this is something very important fact. Okay. This is again, you use this fact that any given permutation is product of adjacent permutations. So using that you can check that if you permute G1 etc. GR, still you will get isomorphic groups. Okay. So that's what we have actually repeatedly used in this, going from one version to another version. So now I will actually make one important comment. So we will actually prove the first version of the structure theorem of finite abelian groups. Okay. So now if you use Sylow's theorem, so the Sylow's theorem guarantees that if you start with the group G, so let us say the order of the group is n and then it has this prime factorization Q1 power some E1 etc. QR power ER, where Qi's are all distinct prime powers, distinct primes. So then what happens for given this I, so given I from 1 to R, so you have there exists a subgroup Hi of G such that the order of Hi is equal to Qi power Ei. Okay, this is what guaranteed by the first Sylus theorem. Now, if you assume G is a finite abelian group, then what happens? So, if you assume G is finite abelian group, then if you collect all these Hi's, you can easily see that G must be isomorphic to this H1 cross etc. cross HR. Okay. So, why this is true? First of all, the cardinalities are same. Okay, the cardinality of G is same as the cardinality of the product of this Hi for I equal to 1 to R. Now, it is easy to see if you take this Hi intersection, this H1 etc. Hi minus 1 cross identity cross Hi cross etc. I plus 1 etc. cross HR. So, that has to be just simply identity. The orders of these two subgroups, they are relatively prime. Okay, I will leave it to you to check. So, check that the order of Hi and order of this particular subgroup, they are relatively prime. So, the intersection of those subgroups must be trivial. So, now if you take the product of Hi, that has to be a subgroup because G is being abelian, all subgroups are normal subgroups. So, in particularly we get G is isomorphic to this H1 etc. HR. So, then now if you want to prove the first version of this structure theorem, then it is enough to actually kind of focus on what is called this P group. So, we can just focus on this Hi. If you prove that this Hi is isomorphic to product of cyclic groups, so then we are done because G itself is product of Hi and each Hi is product of cyclic groups. So, that actually will tell you that our theorem is true for any finite abelian groups. Okay. So, indeed we will reduce to this what is called P groups. Okay. P groups are the groups that having some prime power order P power alpha, let us say, and then we will say that those groups must be product of cyclic groups. Now, using immediate corollary of Sylus theorem, you will get that any finite abelian group must be product of cyclic groups. But anyway, we will also give very explicit proof without using Sylus theorem that G must be isomorphic to product of these P groups for various prime devices P of G. Okay. Okay, so we will actually continue with the proof in the next lecture. I will actually wind up now. So, what remains to prove? Only that G can be written as a product of some P groups, and then each P group is product of cyclic groups. These are the two things that we need to prove in order to prove the first version of first version of this structure theorem of finite abelian groups. Okay, I will stop here. We will continue in the next class. Thank you.